Hi, everyone. I'm Boyuan. Today I will talk about flex attention for inference. This is a joint work from Joy. Joy is sitting here, and I'm Boyuan, and Jason is sitting here, and we also have Yanbo Horace, who is not here today. So we all know the paper attention is all you need, right? This becomes even more true over the recent years. And flash attention is the most important optimization for attention. It makes it much faster, and many people use it, right? And because attention is very important, so we have many different attention variants, like the relative position, document attention, sliding window, etc. It's very hard to write a kernel for every attention variant, right? It's very hard to hand-tune all the variants. That's why we want flex attention. So for attention, we have the QKV, then we have this computation, QK transpose, get the score matrix and the softmax, right? So this is the attention. And for the flex attention, we allow a score mode on the this score matrix so you can modify it in whatever way. And most of the attention variants can be simply expressed in this score mode. So this flex attention is basically have a score modification. It modifies the score for every indices. Also, it has a mask modification that skips computation for certain indices. It supports forward, backward, means you can use it for training, right? We have talked about it last year PTC 2024. And I want to talk about something new we have done over the past year for inference. Why inference is different? Because there is a unique attention pattern for inference. Like the query sentence is usually very short, like one token attends to a super long k value cache, right? The context length could be super long. Because the query sequence length is short, it's hard to use parallelism on this dimension, right? But we still want the parallelism to make it faster. That's why we have the split K optimization from the flash decoding. This is the work from Tridao. So basically, we split on the KV length dimension, like split into these 5 splits, and we compute some output for every partition, every split. And then there is a reduction step to get the final output. Right. Similarly, we have the flex decoding using also with the split K optimization, make it very fast for the inference setting, but we still allow the flexibility from flex attention. Like we can still apply a score mode here, and compute the result for every split, and finally reduce it. Okay, this is the flex decoding. So flex decoding shares the same API as flex attention. We can automatically switch to flex decoding if it's profitable, like the query length is very short. A little bit on the kernel benchmark. Here we compare with flash decoding and also the PyTorch SDPA. It's actually on par with the flash decoding, and it's much faster than the SDPA for this inference setting. Also, we have some model level benchmark on the GPT-fast. We can see some decent amount of speed up over the SDPA. Okay, so now we know that flex attention works for inference. And for inference, people usually want page attention, right? So could flex attention works with page attention? Or do we need a new kernel? Actually, we can. So before I talk about how flex attention works with page attention, I want to give a little bit background on the page attention. So for attention, we have the KV cache, right? We call it, let's say here, we call it a logical KV cache, which is the number of requests times the maximum number of token. Actually, we see some wasted memory here, which is very bad. That's why for the page attention, we have a 1D array of the physical KV cache, right? So we don't have this wasted memory, and we can support a much larger batch size. And in order to map this logical KV cache to the physical KV cache, we have the page table to say, oh, let's say for the request A, the first chunk is mapped to the fourth chunk in the physical KV cache, etc. That's a page table. So how could flex attention works with page attention, right? Do we need a new kernel, or is there any other way? Actually, we don't need a new kernel. We can just do some like block mask conversion to make it work. Let's say for this logical KV cache, we have the block mask, and to say, oh, like for each query, what should be the KV block we should compute, right? And we just need to map to something similar for the physical KV cache, saying, oh, for this query token, what should be the KV index in this physical KV cache instead of the logical KV cache? Yeah, that's why we have this block mask conversion. I give a very simple example here. Let's say for this request A, we have, let's say for this query token, we want to attend to the KV block 1, 2, 4, right? That's why we have this KV index for request A 1, 2, 4. And because we have the page table, we can map it, convert it to the converted KV index, which is the KV index for the physical KV cache, right? We provide a utility function called convert logical block mask to do that. And once we have that, we also need to convert the mask mode a little bit. So people write mask mode on the logical KV cache saying, oh, which logical KV cache index we can skip. So we just need to convert this mask mode, in logical mask mode, into some physical index mask mode. Like here, again, I have one example here. So we say, oh, we take this mask mode and we generate a new mask mode. It takes the batch index, head index, query index, and the physical KV index, right? Based on this physical KV index, we can do some index computation and map it back to the logical KV index. After that, we just call the original user-defined mask mode on this logical KV index, and return this this converted block, converted mask mode, right? Then it could just work out of box. Similarly, we have the score mode conversion. Yeah, so TLDR is flex attention can work with page attention without a new kernel. And about the performance, we compare the flex attention paged version versus non-paged version. Actually, the performance is on par with very minimal latency overhead. At the same time, we can achieve much higher batch size. We have an end-to-end example here in the attention gem. Yeah, so more story on the adoption side. Driss has enabled flex attention, page attention for the VRM v1, which is great. Some OSS user, Jonathan Chang, he or she has a Flex Nano VRM adoption. Use flex attention to build some small inference engine, for the LLM. And we also see more adoptions recently from different OSS users, like MacShow built something for their training, and we have the Andrew Carr and Fern for the Nano GPT training speed run, for the Hugging Face and Jia Chen and Nathan. So basically, we have more and more adoption and some early feedback. So so thanks for your attention. We have a flex attention blog and a flex attention for inference blog. We have more examples in the attention gem and MLC's 25 paper. Yeah, that's all for my talk. Any question? Oh, okay. So currently we have a create block mask function, so you can use it to generate the block mask. And it's suggested to wrap it with total compile. This would make it much better, right? At the same time, you are feel free to write your custom function to generate the block mask by yourself. Yeah. So because for the create block mask, we cannot make any assumption, right, on the block mask. We don't have the semantic knowledge, like, oh, this is the causal mask or what. So we have to generate the, kind of get the value for each index and get the final block mask, right? That's the general way. But you can write your custom one to make it more efficient for your very special mask use case. Oh, at the same time, I want to say that for transformer, usually we have the same attention for many, many layers, right? So you only need to generate the block mask once for all the layers, then you can reuse. If it's 80 layers or something, you can amortize the cost of the block mask creation.